Module 12, Energy, Heat, and Temperature. Calorimetry. Now that you're a bit more familiar with specific heats, there is one specific heat value you do need to memorize. It is the specific heat of water. The specific heat of water is 1.000 calories per grams degrees Celsius, or 4.184 joules per grams degrees Celsius. Notice those two numbers. We defined a calorie as the amount of heat necessary to raise 1 gram of water 1 degree Celsius. And we also defined that 1 calorie equals 4.184 joules. So hopefully, these two values will be easy to memorize. How do chemists know what all these specific heat values are? Looking at the units of specific heat, you can see that we need to know 3 measurements: the mass of an object, its temperature change, and how much energy it has taken in. More specifically, look at equation 12.1. How can we measure these values? Well, we can measure mass with a balance. That's pretty straightforward. What about delta T? That is a change in temperature. So we need to know the original temperature of our object and then the final temperature afterwards. We can measure temperature with a thermometer if our material is a liquid or a gas. But what about solid? That's a little trickier. One way to do this is if we measure the temperature of the environment around the solid. You see, if we let the solid sit in one spot for a bit, then the heat it has will transfer to the environment around it until they are the same temperature. So for specific heat, we need to have 2 different environments at 2 different temperatures. That way we will also have the delta T. But how do we figure out how much energy the object is holding? How do we find Q? We don't have any instruments to measure that value. There is no Q-o-meter. Well, we can measure how much heat the object's environment absorbs because this quantity of heat came from the object. When scientists do these types of experiments, it's called calorimetry. They use a device called a calorimeter, which is an insulated container that holds a known mass of water. There's a thermometer in the water to continually measure temperature. There is also a stirring rod to keep the water circulating for even heat distribution. When a hot object is added to the calorimeter, it releases heat. The water and the calorimeter absorb the heat, and the thermometer will identify that heat transfer by increasing. The water and calorimeter will warm up and the object will cool down. Eventually, they will all reach the same temperature and no more heat will be transferred out of the object. So the temperature measured by the thermometer will stop increasing. That is when the experiment is completed. So there's a measured temperature before the experiment begins and a measured temperature at the end. That will be our delta T. The specific heat of the water is a known, and the specific heat of the calorimeter is also a known. The mass of both the water and the calorimeter can be measured too. So we can use equation 12.1 to calculate the total amount of heat the object emitted to the water and the calorimeter. In fact, we can show that in equation 12.3, negative Q of the object equals the Q of water plus the Q of the calorimeter. This equation says that the amount of heat lost by the object will be equal to the amount of heat taken in by the water plus the amount of heat taken in by the calorimeter. That is why there's a negative sign in front of it. We call this equation the calorimetry equation because it lets us know that any heat gained by the calorimeter and water has to be equal to the amount of heat lost by the object placed in the calorimeter. So the negative Q value represents energy lost. The water and calorimeter are gaining heat, so their values will be positive. Let's go over this new information using an example. A chemical reaction is carried out in a 5.0 gram calorimeter. The calorimeter has a specific heat of 1.95 joules per grams degrees Celsius and is filled with 150.0 grams of water. If the temperature of the water was 24 degrees Celsius before the reaction took place and it rose to 32.0 degrees Celsius by the end of the experiment, how much heat was released by the reaction? Okay, we can treat our chemical reaction as the object that is releasing heat into the calorimeter. We are asked to figure out how much heat was released by the reaction. That means we need to know how much heat the object or reaction released to the calorimeter and the water. Well, equation 12.3 tells us that the heat gained by the calorimeter and the water will be equal to the heat lost by the object. So if we can find the Q value for the water and for the calorimeter, we can calculate how much heat the object lost. How do we find the Q values? We can use equation 12.1 to calculate heat gained or lost by a substance. To do that, we need the mass of that substance, its specific heat, and the change in its temperature. We're given the information for those values for both the water and the calorimeter. The mass of the calorimeter is 5.0 grams, and its specific heat is 1.95 joules per grams degrees Celsius. The mass of water is 150.0 grams, and we know the specific heat of water is 4.184 joules per grams degrees Celsius. We can calculate our change in temperature. Delta T equals the final temperature minus the initial temperature, or 32.0 degrees Celsius minus 24.0 degrees Celsius, which is 8.0 degrees Celsius. Our answer needs to be written to the tenths place. This change in temperature will be the same for the water and for the calorimeter. Let's check our units to make sure they agree with the units for specific heat. And they do. Now we can find the heat gained by the calorimeter. Q equals m times C times delta T. Plugging in our values and canceling out like units, we get a Q for the calorimeter as 78 joules. Let's put that here. The heat gained by water will be calculated the same way. Plugging in our values and canceling units, we get a Q of water as 5.0 times 10 to the third joules. Let's put that here. Now that we have the heat gained by the calorimeter and the water, we can use equation 12.3 to find how much heat the object lost. Remember, the amount of heat lost by the object has to equal the amount of heat gained by the water and calorimeter, because energy is never created or destroyed. Plugging in our values, we get negative Q of the object equals 5,078 joules. Let's first round that number to two significant figures, so negative Q of the object equals 5,100 joules. That means that positive Q of the object will be negative 5,100 joules. The negative sign tells us the object lost 5,100 joules of energy to the calorimeter and water. Let's look at one more problem together. A 28.5 gram block of an unknown metal is heated to a temperature of 151.7 degrees Celsius. It is then dropped into the same calorimeter that was used in the previous example, where mass equals 5.0 grams, specific heat equals 1.95 joules per grams degrees Celsius, and the mass of water equals 150.0 grams. If the initial temperature of the water was 22.0 degrees Celsius and its final temperature was 24.2 degrees Celsius, what is the specific heat of the metal and what is its identity? We need to find the specific heat of the unknown metal and also the metal's identity. Well, when we calculate the specific heat, we can use table 12.1 to look up what the metal is, because remember, each substance has a unique specific heat. We can calculate the specific heat of the unknown metal if we can figure out how much heat it lost to the calorimeter and to the water. So we will be using equation 12.3. We're given enough information to find out how much heat the calorimeter and water absorbed. The calorimeter has a mass of 5.0 grams and a specific heat of 1.95 joules per grams degrees Celsius. The mass of water is 150.0 grams and a known specific heat of 4.184 joules per grams degrees Celsius. We need to calculate the change in temperature. Delta T equals final temperature minus initial temperature, or 24.2 degrees Celsius minus 22.0 degrees Celsius. That is 2.2 degrees Celsius. That can go in both columns. Now we can find the amount of heat the calorimeter gained. Q of the calorimeter equals m times C times delta T. Plugging in our values and canceling out like units, we get a Q value for the calorimeter as 21 joules. For the Q of the water, we can do the same thing, and we get 1,400 joules. We can now use equation 12.3 to find out how much heat the object lost. Remember, the amount of heat the object lost to the calorimeter and the water has to be equal to the amount of heat the calorimeter and water gained. So negative Q of the metal equals Q of the water plus Q of the calorimeter, or 1,400 joules plus 21 joules, which equals 1,421 joules. Now we need to round that number to the hundredths place, so we get negative Q of the metal equals 1,400 joules. That means the Q of the metal equals negative 1,400 joules, or the metal lost 1,400 joules of heat. So we have the heat lost by the metal. Now what do? Well, we need to find its specific heat. Looking at equation 12.1, if we have the mass of the metal, its heat lost, and the change in temperature, we can find its specific heat. Well, we have the Q of the metal. We're given the metal's mass at 28.5 grams. What is its change in temperature? We know its initial temperature was 151.7 degrees Celsius before it was placed in the calorimeter. We also know its final temperature because it will be the same as the final temperature in the experiment. So the change in temperature of the metal equals the final temperature minus the initial temperature, or 24.2 degrees Celsius minus 151.7 degrees Celsius, or negative 127.5 degrees Celsius. It's a negative value because when the metal was added to the water in the calorimeter, it cooled down or lost heat. Now let's rearrange the equation 12.1 to solve for specific heat, and we get C equals Q divided by M times delta T. Plugging in our values, we get specific heat of 0.39 joules per grams degrees Celsius. That's the first part of our answer. We can now refer to table 12.1 to see what metal has this value for specific heat, and we find that it has to be copper. Now, though this was an involved problem, we first approached it knowing that it involved calorimetry. That means we had to use our three equations, and we had to think through what was occurring in the experiment to know what to do. We know that the object released heat to the calorimeter and the water. They took in heat. So if we could figure out how much heat they gained, we would know how much heat the object lost. Now there's one more thing I want to point out in this problem. When we calculated the heat absorbed by the calorimeter and the water, and we added those values together, you might have noticed that the heat absorbed by the calorimeter was so small it didn't change the value once we considered significant figures. This is common with calorimetry experiments. Often we don't even consider the heat the calorimeter absorbs because it is so small as compared to how much heat the water absorbs. So often we can ignore the calorimeter calculations. But if you are given information about the calorimeter, including its mass and specific heat, then you need to make sure you do consider the heat it absorbed when you do your calculations. When you do experiment 12.2, you will understand this better. Module 12, Energy, Heat, and Temperature. Experiment 12.2. This lab's going to help us to actually figure out the specific heat of a metal. And to do that, we're going to use a calorimeter and calorimetry. The first thing I'm going to do is I've got some water getting ready to start boiling. And while that's boiling, I'm going to do a couple different things. I'm first going to take the metal. This is the metal we'll be using, which is a lead sinker weight. And I want to measure its mass. So I'm going to go ahead and put it on my scale. First, I'm going to make sure that my scale is zeroed out before I do that. And it is. Get a little more accurate here. There we go. Set it in. Measure my mass in grams. And okay, it's 87.2 grams. All right, now that I have that, I'm going to put the metal, this is just now getting ready to start boiling, so I'm going to go ahead and put my metal in there. I want to get the metal up to a boiling temperature. I'm going to carefully put it in with some tongs. You don't want to drop a heavy weight metal sinker into glass. You could be doing this in your kitchen, using a pot on the stove. If you do, I would recommend you use an old pot that you're not going to use for cooking because we're working with lead. If you have a lead weight and you don't want lead to get onto the pot. Now you can use other kinds of metal that aren't lead for your weights, and if that's the case, you don't have to worry about it. But with lead, you don't want to use it with cooking materials. All right, so since I'm using my beaker, I'm good to go. Now that I've got that heating up, I want this to be heating up to a temperature of 100 degrees Celsius. I'm going to wait until my water's boiling before I pull that out. While it's heating, I've got my 2 styrofoam cups to make my calorimeter. That's all it takes to make a calorimeter, just 2 styrofoam cups, one in each other. And I want to measure the mass of my calorimeter with my scale. Just empty. And for all practical purposes, let's see. Yeah, it's about 0.2 grams. So let me write the mass of the calorimeter. Okay, now I'm going to fill the calorimeter with water, just regular room temperature water, which I have over here. And I'm going to fill it about 3/4 of the way full. And I want to measure the mass of my water. To do that, I'll take the mass of the calorimeter in the water, measure that, and then subtract that measurement, subtract the mass of the calorimeter from that measurement. So the mass of the calorimeter and the water, 125, 35, looks like 139.0 grams. And so if I take 139.0, subtracting 0.2 grams of that calorimeter, and I get 138.8. All right. Erase my calculations to make it look neat again. Okay, and I'm getting some nice boiling water there. I want to keep that in there just a few more seconds. And let's see what we have here with our book here. Okay, now I want to measure the temperature of my water in the calorimeter before I do anything, my initial temperature. So I want that to sit for a good 3 minutes and let it get to the same temperature as the water. And this is boiling. And then once it's done, once I get this temperature, I'm going to transfer my heated metal object into my calorimeter and see how that heat transfer changes. So let's go a little bit longer. And since everything has been at room temperature, including my thermometer and my water, I can go ahead and take that temperature now. And I've got 26.4 degrees Celsius. That's my initial temperature. That's the temperature I'm starting out with. Okay, 26.4 degrees Celsius. Okay, now you can see that my water is boiling nicely with my metal, and it's been in there long enough now to have come to the same temperature as the water, which is boiling temperature, 100 degrees Celsius. I'm going to turn this off. And I'm going to carefully transfer this to my tray so I don't spill anything. And then it makes my transfer a little bit easier. Okay, hot metal going into my calorimeter. And I'm going to stir it with my thermometer, not letting my thermometer touch that metal because I don't want that to affect my readings. And you're just going to watch your temperature reading in your thermometer until you get it to level out at one temperature. Let me double check and make sure I'm on track. What we're seeing here is as the temperature is increasing, the heat in the metal is transferring to the water. So we're seeing a heat transfer, and that makes the water temperature then go up. Should make sense to you, right? We just take getting the water hot and give it some fun names like calorimetry. Okay. Wait a few more seconds here and see if it stabilizes. Staying the same. Okay, so my final temperature here is right on the dot at 28.0 degrees Celsius. So I'm going to write that down, 28.0 degrees Celsius. So what happened with the water is initially it was 26.4 degrees Celsius and it went up to 28.0 degrees Celsius. So I now need to grab my calculator here, and to find the difference, it's final minus initial. So we have 28.0 subtracting 26.4, and we get 1.6 degrees Celsius. as our change in temperature from the water. We're ignoring the calorimeter in this lab because it's negligible. All right, now that we have that, we actually can calculate the heat transferred from, or heat change from our water. So I can do the Q of the water, which are using our formula Q equals M times C times delta T as our formula. We have the mass of our water. We have the C of our water as a given, 4.184 joules over grams Celsius. And then we have our change in temperature, which we just figured out to give us our Q, or our heat that the water took in, okay? Remember that we put the metal in there and the water took in heat. We're calculating what that is. So our Q of water is the mass of water times C, 4.184, and that's joules over grams degrees Celsius, times our change in temperature, 1.6 degrees Celsius. Let me run those numbers. 138.8. Use your significant figures here. And I'm going to the 10th place, 929.2. What are our units? Well, I have grams in the numerator, grams in the denominator here. Those are going to cancel. And then I have Celsius in the numerator, Celsius in the denominator, which is canceling. I'm left with joules. Okay, so this is my Q of the water. Okay, now we can use our next equation to determine if this was the water heat absorption, how much heat was the metal releasing. So I can use the formula negative Q of the object equals the Q of the water plus the Q of the calorimeter. In this case, we're ignoring the calorimeter, so we're basically saying the negative Q of the object is the Q of the water. So what we have is negative Q of the object equals 929.2 joules. Therefore, the Q of the object, the heat of the object, is a negative number, negative 929.2 joules. And that should make sense to you. Okay, what that's saying is the object lost heat. We took a hot piece of metal and stuck it in room temperature water. The metal lost heat to the water. The water gained heat. That's why the water has a positive Q. Okay, now that we have the Q value for the object, we can calculate its specific heat, which is a C. We're going back to this formula. We want to find the C, which is specific heat for that metal. And we have the Q of the metal, we have the mass of the metal, and we need to calculate the change in temperature of the metal. Well, let's get the change in temperature first. The initial temperature of the metal was boiling water temperature, right? We started that boiling water temperature, and we put it into our calorimeter. Well, what's the temperature of boiling water? 100 degrees Celsius. The final temperature of the metal will be the same temperature as what the water was as a final temperature, because as the metal lost heat to the water, both the metal and the water had the same temperature at the end of our experiment. So the final temperature of the metal is the same as the final temperature of our water. Okay, so now I can calculate the change in temperature of our metal, which is 100 subtracting 28, and that's 72. Okay, which I can do to the 10th place. Always got to watch those significant figures. All right, now we can finally do our final calculation. I'm going to rearrange this formula so I'm solving for C. So C equals Q divided by mass times delta T. I'm going to plug in my numbers. My Q of this is the C of the metal. I'm going to put a little M there. So the Q of my metal, I just calculated it, as negative 929.25, and I need to use my units, joules, okay? Put that over the mass of my metal. Where's the mass of my metal? I figured that out up at the beginning, 87.2 grams. And then my delta T, or the change in temperature of my metal, which is 72 degrees. Notice the units of what my C is going to be. Joules over grams times degrees Celsius. And that's the unit that we want our specific heat to be in, so we're on track. Let me run the numbers. $929.2, and that's a negative number. Okay, and I can only take this to the tenths place, so I want to round to the tenths place. My negative is going to be, negative 0.1, actually negative 0.2. Negative 0.2 joules over grams degrees Celsius. Now let me just check that negative sign one more time. Aha. This should not be negative, and here's the reason why. This is something you have to check yourself to expect it. When I calculated my temperature change, it's final minus initial. So it's 28 minus 100, which means this temperature change is a negative temperature change. Therefore, this 72 is negative. My negative over my negative makes this a positive. We should always have a positive specific heat, and that was how I reminded myself, oops, I made a mistake. And that's okay as long as you know what to expect, which is why you use your units to check yourself and also have an idea of what kind of value your answer is supposed to be in. So this right here is our answer of specific heat of that metal that we began with. Energy transfer is important, isn't it? I can feel that solar energy from the sun on my body right now as I'm standing in the desert, as well as what's reflected off the sand. Now I can minimize that heat transfer if I used a big beach umbrella, couldn't I? Well, hopefully you have a good understanding of energy, heat, and temperature now after this module. We're going to study those subjects more in the next module. So for now, make sure you understand the process of calorimetry. As long as you have a good idea of what's happening with the heat movement when you add that hot object to a calorimeter, you'll have a better understanding of the process that's going on.